muscle tissue, and I took a look at some capillaries that are right next to it, just running right through that tissue, and I measured the partial pressure of carbon dioxide in the fluid that is part of the muscle tissue, and I measured the partial pressure of carbon dioxide in the blood that's flowing through there, I'd see there's a gradient. The partial pressure of CO2 is higher here than it is there, because that tissue's cranking out CO2. So, if the partial pressure of CO2 is higher here than it is there, what's going to happen to the CO2? It's going to diffuse into the blood, right? Simple diffusion, right across, that's supposed to be a capillary membrane there. Right across the capillary wall into the blood, because there's more here than there, simple diffusion. The same thing would happen here. The gradient's not as steep, but there's still more here than there is there. So either way, we just dumped a bunch of carbon dioxide in the blood. All right, fine. So we got a bunch of carbon dioxide in the blood. I'll write it again. Well, the blood is mostly water. It's the whole blood, peripheral blood, is something like 55% plasma by volume, and the plasma is the liquid part of the blood. Plasma is about 93% water, so whatever 93% of 55 is, that's the percentage. It's about half water. Okay, so when you put CO2 in water, this could be in your blood, it could be me standing here with a beaker of water and a tank of carbon dioxide gas with a tube going into it. Either way, when I combine carbon dioxide with water, what do I get? If you had me from 105 last semester, you better know the answer to this question because it was on every single freaking exam I gave you. Please tell me that the people in last semester's class remember this reaction where CO2 and water got together and did something. Equilibrium? What? Yes, thank you. Carbonic acid. Carbonic acid. Carbonic acid. It looks like this. Remember you saw that reaction over and over and over and over until you were sick to death of it? If you were in my class, you did. I have the exams to prove it. What's that?
I probably got those questions wrong in every test.
All the more reason to remember it. You wouldn't have been the only one either, so that's okay. Carbon dioxide plus water gives you that stuff. Carbonic acid. Oh yeah, you guys in ecology. Carbon cycle, come on, we just did this like 3 weeks ago. See, I'm out to play for people today. Not really. Carbonic acid, that's carbonic acid. I can sit here with a beaker full of water and a tank of carbon dioxide and bubble it through there and I'll make a little bit of carbonic acid. It's just a reaction that happens. I can sit here with CO2 in a tissue, dump it into the blood, which is mostly water, and that reaction will happen. Carbonic acid. But there's a catch. Most of the CO2 that gets in here, this reaction happens, but it's not terribly likely to happen. If I wanted this reaction to be extremely likely to happen, what should I add to the picture? What? An enzyme, yes. Doesn't that make reactions more likely to happen? Well, guess what? You've got an enzyme in here that makes that reaction, and it catalyzes that reaction. So yeah, I can sit here with a beaker and bubble it through and make a little bit of carbonic acid. But if I want to ensure that this reaction happens, and there's a reason why I do, I'll show you, throw an enzyme into the picture. Well, watch what really happens here. This occurs, but the CO2 and water really react with each other while they are in a red blood cell. That blue sort of oval-shaped thing that I just drew is supposed to represent a red blood cell. There are trillions of them in your circulatory system. They're not really that big. That's just one of them, okay? So what really happens is this. The CO2 diffuses, simple diffusion, into the red blood cell, and of course there's water inside the red blood cell too. And this reaction happens extremely readily because there is an enzyme that catalyzes it. I will just write its abbreviation here, CA, and because I have more room up there, I will write its full name. Carbonic anhydrase. Ends in ASE, so it must be an enzyme. So, just to back up for a second. Your red blood cells have loads of this enzyme called carbonic anhydrase. It catalyzes that reaction. So will a tiny bit of the carbon dioxide that just immediately gets into the plasma react? It's insignificant though. Will a tiny bit of it just stay dissolved out here? Yeah, maybe 5%, 7% actually of it just stays dissolved. But the vast majority of the CO2 that gets into the blood gets immediately sucked into the red blood cell by diffusion and combined with water, thanks to this enzyme, and now you got carbonic acid inside the red blood cell. Does a little of that happen out here without the enzyme? Yeah, a lot of it happens in here. Just a little side thing on carbonic anhydrase. Of all of the thousands of enzymes in your body, that is the one that has the fastest turnover number. The turnover number is basically how fast the enzyme works. How many reactants can it turn into products per second? And that by far is the fastest working enzyme in your body. It's one of the fastest working enzymes known. It works insanely efficiently. Anyhow, so as soon as that CO2 hits a red blood cell, it's getting turned into carbonic acid. Well, carbonic acid is an acid. It's redundant. So what does that mean? If I'm in an aqueous environment and this is an acid, what happens to it?
pH decreases.
True. What am I going to write over here to express what you just said? What's the definition of an acid? What?
Plus H plus.
Please tell me that reaction looks familiar. If you were in my class last semester.
I remember now.
Yeah, that one. See. Go back and look on those old exams. They kept showing up, right? So carbonic acid is an acid. By definition, acids are proton donors, right? They dissociate when they hit water and turn into a proton, that is a hydrogen ion, and some anion. That is a spontaneous reaction that does not need to be catalyzed. So as soon as this happens, this happens. Now this is a reversible reaction, they're both reversible reactions. But now I've got this stuff and this stuff sitting around. So I got this whole chemistry happening in a red blood cell. There's even an enzyme involved in it. So you say, well, why do all this? Well, if I didn't do any of that, if I just said, hey, go ahead, muscle tissue, dump your CO2 into the blood, a little bit of the CO2 would dissolve in the blood, a little bit of it would react, but without that enzyme, it's limited. In other words, the CO2 carrying capacity in the blood would be extremely limited. You wouldn't be able to carry nearly as much as you need to. You're producing a lot of it. You want to get it into the blood and use the blood as a conduit to get the CO2 to the lungs so you can exhale it. If it stayed CO2, you would never be able to conduct it that readily. The CO2 would all back up. It would all hang around here. It wouldn't get transported the way it needs to. So you have to convert it ultimately to that. Because look, there's a carbon and a couple oxygens built into that ion. So the CO2 that came out of these tissues, ultimately, there's the carbon atom and two of those oxygen atoms are those two. You just had to turn it into this instead. If that's not clear why yet, I will restate it in a different way, but that's what happens to it. By the way, that ion has a name. Anybody remember? Bicarbonate ion. That's a bicarbonate ion, HCO3 with a minus sign. So that's the chemistry. Now, you say, oh, well, if I put a CO2 molecule, remember, partial pressure, high concentration, low concentration, the thing that's making this happen, the thing that's essentially sucking the CO2 out of the tissue is the gradient. If the concentrations here were equal, that wouldn't happen. If the concentration here were greater than there, the reverse would happen. You want this to happen. So, as soon as the CO2 hits the blood, the majority of it gets pulled into a red blood cell and turned into something other than CO2. Which means that CO2 that was there for just an instant isn't there anymore. I maintain the gradient. So if I take a CO2 out of here and put it in here, like that, but then it turns into something else, and I do that again and again and again, I always have a gradient. If I didn't, if I just took the CO2 out of here and put it here, that would happen. And diffusion from here to here would stop. This tissue would die in its own CO2. But because I have this enzyme and these red blood cells and all of that chemistry, I can get the CO2 to turn into something else. That way I can always keep a draw on the CO2 as the blood flows past the tissue. CO2 is always going to want to jump into the blood and not stay laid in the tissue. That's exactly what I want. Does that make sense so far? Okay, but there's one other problem. It's fixable, but it's a problem. If this just lays around in here, think about equilibrium. That's why I use this equation over and over and over when we studied equilibrium last semester. Think about equilibrium. If this is a closed container, eventually, won't this system reach equilibrium? Won't this system reach equilibrium where I have a constant ratio of these to these to these? Yeah. If that's the case, I'm going to lose my ability to pull more CO2 out of the tissue. I want to keep a draw on this entire reaction. I want to make sure that this happens and not that. This could happen. I don't want it to right now because I want to keep the CO2 getting sucked into the red blood cell. So what do I have to do? As if this stuff just accumulates in this red blood cell, it goes up and up and up, then this slows down, then this slows down, then this slows down, then this slows down, and I stop pulling CO2 out of the tissue. So what do I have to do to this stuff? Get it out of the red blood cell. Because if I throw one of these out, another one of these will happen, and another one of these will happen, and another one of these will happen, and another one of these will happen. For every one of these I throw out of the red blood cell, I pull another CO2 out of the tissue. I want to keep pulling CO2 out of the tissue. So I got to find a way to get that stuff out of the red blood cell. There is a protein that helps me do that. I'll draw it as a big blue dot. There are lots of them in the membrane. That protein is going to facilitate the diffusion of bicarbonate ion out of the red blood cell into the plasma of the blood. It's an ion, it's soluble in the blood. So as soon as you make that that bicarbonate ion, it diffuses out into the blood. And that's where your CO2 is. This happens instantaneously. This happens in a fraction of a second. So the CO2 gets produced here, into the blood cell, turns into carbonic acid, turns into bicarbonate ion gets thrown into the plasma. The majority, 90+% of the CO2 that is traveling in your blood is traveling in that format. Not as dissolved CO2, a tiny bit of it's dissolved CO2, but it's as bicarbonate ion in the plasma. And as rapidly as I throw this into the plasma, I suck another CO2 into the red blood cell and therefore suck another CO2 out of the tissue. And that's what I want to keep doing. There's still one problem though. If I just throw negative ions out of here and don't do anything, think about what's going to happen to the ion gradient across this membrane. Taking negative things out of here, put them out here. This is going to get less and less and less negative. That's going to get more and more and more negative. There's going to start to be an ion gradient, a charge gradient across that membrane, and the cell's going to freak out. It's not going to know what to do with that. It's not going to be good for the cell. So, to make sure that the charges stay the same, that I don't have too many negative things out here or too few negative things in there, what would you like to do? Every time you throw out a negative bicarbonate, what might you choose to do to nullify that negative charge exiting? You could, but there's another way. Rather than throwing a positive out with it, what else could you do? Pull in another negative. I heard somebody say it. See who said it. But pull in another negative thing to cancel it, right? So there happens to be an abundance of those ions in the plasma of your blood. Those are chloride ions. Tons of them hanging around. They're negative. That very same protein that exports the bicarbonate ion simultaneously imports the chloride ion, and it's a one-for-one exchange. In other words, I don't worry about the charge gradient or the membrane potential changing, because every time I throw out a negative ion, I bring back another different negative ion, so that's okay. that notion that you see there, the fact that I bring chloride in for every bicarbonate that goes out, is a notion referred to as the chloride shift. If you look up the phrase chloride shift in the index of your textbook, you will go right to the page that has this picture on it. I don't know what page number that is, but it'll be easy to find. Or just Google the term chloride shift. You'll find this, okay? So now I don't have to worry, oh my God, I screwed up the charges, and the cell membrane is not gonna like that. It's not gonna happen. So I found a way to keep a constant draw, a passive draw, that's diffusion. I'm getting the CO2 out of the tissue. I had to do a little chemistry to make that happen. I had to turn my CO2 into bicarbonate ion, that's okay. If you're wondering, hey, what about those protons that are accumulating inside that cell? That doesn't seem like a good idea to just have protons stashed away. That means the pH of the contents of the cell is going to go down and down and down. It's not, because those protons glom onto proteins in the cell. I'll tell you which one mainly in a second. They glom onto proteins and are quenched. They're nullified. So you don't have to worry. What looks like an acidification of the contents of the cell really won't be, because there are proteins in there that buffer those things. Remember buffers? Buffers are good too. That was chapter 3. That was a long time ago. Buffers was like, what, September? That was a long time ago. Anyway, that's the chemistry of how to get CO2 out of your tissue into the blood. Isn't that awesome? That's why I kept using that reaction over and over and over last semester, because I knew you'd need to see it again this semester. Well, what happens when this blood eventually makes its way to a capillary in the lung? Well, now I want to exhale carbon dioxide, but I don't have carbon dioxide. I got bicarbonate ions floating around my plasma. I can't exhale an ion. I need to exhale gases and vapors. That's an ion dissolved in water. I'm stuck. Well, not really. Because remember, you have a capillary here. This is the capillary. And you have a type 1 pneumocyte here. So to go from this compartment, your blood, to that compartment, the airspace in an alveolus, you're going through 2 thin cells. The endothelial cell of the capillary and the type 1 pneumocyte of the lung. Well, you can do some chemistry in those cells. What happens now is this. The partial pressure of CO2 in the airspace, the alveoli of the lungs, is much lower than the partial pressure of CO2 here, which means CO2 is going to want to do that passively, right? But the CO2 is in this format right now. Without the help of enzymes, if this stuff diffuses into the capillary cytoplasm and into the type 1 pneumocyte cytoplasm, this reaction will be reversed. Just equilibrium is going to make that happen. Just the law of mass action, remember that? The law of mass action is going to make that happen. So that by the time this bicarbonate ion crosses those 2 cells, what gets deposited into the airspace, that is the alveolus of the lung, is carbon dioxide gas and water vapor. Because, well, that's really what that is, isn't it? So I get CO2 and water vapor back there. It's just the reverse of this. I won't redraw the same reaction. It's just that backwards happening in those cells as this stuff is moving across passively. Can I exhale carbon dioxide gas? Sure. Can I exhale water vapor? Sure. That's the CO2 and much of the CO2 and water vapor that you're exhaling right now is there because of that reverse reaction. I exhale it, the CO2 goes away, it's gone out of my body, which means this, according to the law of mass action, is going to keep on happening. Isn't that awesome? It's a beautiful thing. Okay. Questions on that? I'm glad you showed up today. I missed this one. In addition to the packet, I have another handout from another book that I like. I think they do a really good cartoonish job of it. Like the way they draw this is really good. I'll see if I can Xerox that for you as well. But our book has this. I mean, look in our textbook. Okay. All right. So we figured out how to get CO2 from the tissue through the blood to the lungs and exhale it. We need to get oxygen from the air into the lungs, into the blood, to the tissue. We do the opposite with oxygen. But it's a very different story than this story. So I'm about to erase that red blood cell and all that chemistry so I can draw the revert, I can draw the oxygen coming in instead of the CO2 going out. Before I do that, however, let me just point out one thing. Like I said, the vast, vast majority of the CO2 that goes from here to here gets sucked into the red blood cell. Something like 93% of it does that. The remaining 7 or so percent of the CO2 that gets dumped into the blood just stays dissolved in the plasma, and even without the carbonic anhydrase, some of it will react and give you, we'll give you that, this is 2 reactions here. In other words, this will happen without carbonic anhydrase, just not very fast. A little bit of, like I said, about 7% of the CO2 that gets dumped in here, it'll just do that on its own. Seemingly insignificant, but if I do enough of this, if there's enough CO2 getting dumped out of here into the plasma in a neighboring capillary, I'm starting to accumulate those. More of those means what? pH is going to change. Is it up or down? It's going to go down, right? More acidic, right? So, do you expect the pH of this area right next to the active tissue to be higher or lower than the pH of the plasma right next to the lungs? This is going to be lower. They got a few of these guys building up. Over here, I'm dumping CO2 out by taking these and turning it into CO2. So if I measured the pH of the plasma in a lung capillary and compared it to the pH of the plasma in a capillary in a piece of muscle tissue, there would be slight differences. It's going to be a little higher next to the active tissue, a little bit lower next to the lung, right? In other words, the more active the tissue is, the more acidic the environment is. Make sense? So, big picture. When I exercise a lot, say you go do your kickboxing class for an hour or something like that, and you do some tremendous amount of aerobic activity, lots of muscle activity, etc. Do you think your blood plasma overall, now there's buffers in there, so you shouldn't see significant changes, but did you just contribute to the acidification of your blood plasma by exercising a lot? Yeah, absolutely. Well, how come your blood plasma didn't drop? I mean, if it dropped significantly, you'd have died. So somehow you produced lots of CO2 and therefore lots of carbonic acid, and yet somehow the plasma of your blood stayed pretty much the same pH. Well, there's buffers in your blood. And what else did you do when you exercise? What happened to you? The more you exercise, the faster you breathe, right? If I do this exhalation faster, don't I blow off CO2 faster? Don't I convert this into CO2 faster? Don't I undo this reaction faster? Sure. In other words, by getting rid of CO2, I'm in essence getting rid of something that would acidify my blood. I didn't consciously think, gee, I better breathe faster when I exercise. Somehow, the respiratory centers of my brain and my brainstem back here told my respiratory system to do that. What were they paying attention to? When you exercise, what do you think your respiratory system is looking at, saying, gee, breathe faster?
CO2 concentration or the pH?
pH. It's not oxygen. People usually answer oxygen. Oh, I need more oxygen, that's why I breathe faster. Nope. Your blood pH is starting to drop. That's why you breathe faster. Your respiratory centers say, oh, blood pH is dropping. Must be too much carbonic acid in the blood. How do we get rid of carbonic acid? We do this faster. We take bicarbonate out of the blood, turn it into CO2, and exhale it faster. Well, my pulmonary mechanics have to speed up if I'm going to do that. So I blow off CO2 faster, therefore not allowing my blood pH to acidify like it otherwise would have, because my brain centers are sensitive to pH. My respiratory centers in my brain notice the temporary drop in pH and say, uh-oh, we better start breathing faster. Oh yeah, by the way, we bring more oxygen into the body when we do that too, but that's not why you breathe faster. The trigger for the increased respiratory rate is the instantaneous drop in pH when you exercise. Isn't that exciting? All right. So, what we're gonna do, oh crap, this should be a 2-hour class, I could do so much more. Anyway, let me tell you what we're gonna do on Wednesday. It's gonna have to do with oxygen, okay? We're gonna take oxygen out of here, because 21% of the air you're breathing is oxygen. High partial pressure of oxygen in the alveoli, your lungs. It's gonna diffuse into here, something's gonna happen, and we're gonna be able to deliver it. However, think about this. Do each of these two tissues that I gave as examples, do they need the same amount of oxygen as each other? No. This needs more, this needs less, right?
Yes.
Somehow, my blood and yours has the ability to say, you need more, you can have more. You need less, you can have less. We got to explain how that happens. It's not just a one-size-fits-all and dump off oxygen and hope it's the right amount. There's chemistry in the blood that knows how to deliver exactly the right amount based on supply and demand. You want more? I'll give you more. You want less? I'll give you less. And that's some awesome chemistry too. We will talk about that on Wednesday. Have fun.